Okay. Hello everyone, my name is Xiaotian from Tsinghua University, China. Today my topic is a construction robot path planning method based on safe space and worker trajectory prediction. My presentation will include 5 parts. The first one is the introduction. As we know, the construction industry is facing several problems such as labor shortages, frequent safety incidents, and we know intelligent construction and construction robots are seen as the important way to solve these problems. For each construction robot, the basis to perform the tasks is a safe and efficient path to their destination. However, the dynamic changes at the construction sites pose enormous challenges to their collaboration safety. Therefore, it is necessary to establish a construction robot path planning to deal with this dynamic environment. To address this dynamic path planning problems, a hybrid strategy has received significant attention. The hybrid approach first generate an optimal route based on global path planning and then make some flexible adjustments based on local path planning. However, the method overlooks the trajectory prediction of workers or the other dynamic obstacles, and fails to consider the safe space of the workers and the robots. Most studies lack a comprehensive and effective solution for the path conflict. The predicted trajectories of workers and the other machinery can enhance the efficiency and the safety of the path planning in such a dynamic environment. In current study, the prediction methods can be divided into the physics-based and the learning-based approaches. The physics-based approaches are based on some dynamic or kinematic models, while learning-based can extract the behavior patterns from the historical training data. The physics-based approaches does not rely on massive data from the site, so it is more suitable for the construction environment. And our method involves 4 parts. The first one is map establishment. We extract the necessary information from the build model and the schedule information. We got the grid map with the schedule and the symmetric information. The second part of our method is the improved A-star. Traditional A-star algorithm use the same weights for the G and H function. In our research, we add the dynamic weights W to the H function, which is to consider the characteristics of the construction schedule. The third part of our method is the improved dynamic window approach. In traditional DWA, it only considers the motor performance or braking distance. Besides, the distance and the velocity function are built based on the simple expansion of the obstacle. The dynamic properties of the robots and the future state of the workers are not considered. Therefore, a safe space is defined and created for both workers and robots. We define the worker safe space as the worker operation space, which is WS, and the worker movement space, which is WMS. And the WOS is the static region. WMS is dynamic, which is related to the worker speed. The definition for construction robot safe space is similar. As we know, construction workers are the most common and complex dynamic obstacles at sites. Therefore, predicting worker trajectory can provide abundant information for the path planning, which will make the path more efficient and safe. Different from the traditional prediction, we establish a nonlinear model for the worker. Then the trajectory is predicted based on the cubical Kalman filter. The process is as follows. With this prediction, we can use the trajectory to optimize the DWA's distance function and the velocity range. And the fourth part of our method is the decision model. A path conflict does not mean that the conclusion will happen. The conclusion happens only when the spatial and temporal conflicts occur. So to reduce the unnecessary local path planning, we propose the decision model based on the global path and the predicted trajectory. We can got a area called the potential collision zone, which is PCZ. If there is no PCZs between the two paths, it means the conflicts between the worker and the robot will not happen. So the robot can follow the original global path. If the PCZ exists, it means a special conflict exists. So the decision model will further select a decision. The decisions are as follows. And for different cases, we can choose various decisions to make the path more efficient. For the fourth part, an experiment was conducted to evaluate our method. For the global path planning, we tested the improved A-star on the left picture with the schedule. For the local path planning, we use a vehicle to represent the construction robot and use the humanoid robot to represent the worker. We can see the right picture. From the results, we can see that the improved A-star can successfully plan the global path, and it can plan the path more efficiently, as we can see in the right table. For the two pictures below, we can see the robot path plan, global path planning with the workers' prediction. They will have the PCZ zone. In the left picture, we consider the prediction trajectory. So the robot will find a path behind the worker. And in the left picture, without the prediction, the robot may find the picture in front of the worker. So it may it perhaps cause the secondary collision. So with the prediction, it will make the local path more safe. Yeah. And this one, the first table is compares the prediction results for the worker and the decisions for the robot. The table below summarizes 3 groups of our research, which shows the improved method can achieve a shorter path. To sum up, our research proposed a construction robot path planning. First, we established a grid map based on beam model and the construction schedule. Then an improved A-star is proposed. Besides, we use the safety space and the prediction to improve the DWA algorithm. At last, a decision model for the path conflict was established. After this, we use the case study to evaluate our method. However, there are still some limitations in our future, such as we need to conduct the experiments in the field and consider other distances, such as multiple robots, and make the worker move them more faster to amplify our experiment. Yeah. And these are our references for the paper. Thank you very much for your listening. Thank you.
Thank you, Xiaotian.